afternoon, everyone. Welcome back. So I'm just going to give a brief overview this afternoon on some of the materials that are available for additive manufacturing and 3D printing. I'm going to use those two terms interchangeably throughout my talk. There's really no difference in the processes or the materials. So I'm going to talk a little bit about what's available, what's already out there, what you can buy, and also some of the research, some of the things that are coming, and some of the gaps in the market where there are opportunities. So I'm Rachel Gordon. I work at ID TechX. I lead our research into 3D printing and additive manufacturing, which includes the processes, materials, applications. My background is in originally physical sciences and specializing into material science at Cambridge University. At ID TechX, we cover a range of emerging technologies. So I am predominantly focused on 3D printing, and I also do some of our research into advanced materials, which includes things like graphene, carbon nanotubes, and various adhesives. But we also cover a wide range of topics, all things that we think are new and exciting and coming soon. And actually, this slide's already out of date because we've just very recently included robotics. And at ID TechX, we cover these technologies in 3 different ways. So we do research. This is market research. We write reports based on who makes what, who sells what, who buys what. The technology landscape, the commercial landscape, and forecasts for what is happening in the market soon. We also do bespoke consultancy, so if you have specific questions on how any of these technologies affect your business, we're happy to help you with that. And we also run 2 major events throughout the year, one in Berlin and one in California. So all the information in this presentation is coming from our market research reports. We've got a series on 3D printing, and including a specific report on materials. So here is just a quick overview of the different materials and the different ways that you can print them. So probably most commonly recognized is the thermoplastics. And you can print thermoplastics either by material extrusion, so that's a kind of typical MakerBot style desktop printer, or by a powder bed process, so selective laser sintering. The kind of other idea that comes to mind is often metals. Metals can also be 3D printed in a number of ways, most commonly, again, powder bed process using selective laser melting. But there are actually a number of other materials that you can 3D print in various ways. I'm just going to talk about some of them this afternoon. I'm probably not going to touch on biomaterials very much. There is a whole market around biocompatible materials, materials that can be implanted, materials that can support cells for scaffolding, and even 3D printing of cells. That's very different to typical engineering 3D printing. It uses a lot of different processes. And while I'm happy to talk about it, I'm probably not going to cover it in much detail in the presentation. So the first thing I want to talk about is 3D printing in plastics. So if you decide that you have an object that you want to print in a plastic, you then really have 3 options. So if you're looking for something to be very precise, if you need very fine detail, you're probably going to need to use a photopolymer in a stereolithography type technique. If you need to build something quickly, or if you want something that's going to be strong and tough in your final object, you need to use a thermoplastic powder in a selective laser sintering way. Or if you're looking for something that's very cheap, or something that's very large, you're going to need to use a thermoplastic filament in a material extrusion technique. Okay. I'm just quickly going to talk about photopolymers. So there are a number of machines available on the market that will print in photopolymers. They are typically either stereolithography printers, so this is where you have a big vat of a photopolymer. Then you use a laser to cure the photopolymer in the shape you want, and layer by layer you can build up a 3-dimensional structure. Alternatively, you can use a direct light processing method where you use a projector, and you can project a black and white image onto the whole layer and cure or not different pixels as you like. This has the advantage of being much faster because you can cure a whole layer at a time. These photopolymers are used in a variety of ways, most commonly to produce hearing aids and dental implants and various bits of kind of costume plastic jewelry. And then also, if you're talking about inkjetting of photopolymers, which is the technique that the object machines use, where you inkjet small amounts of photopolymer and cure it at the same time. You can use those things to build mostly prototypes and models because you can get a good range of colors and you can get a good range of, well, a range of different materials with slightly different properties, so some slightly harder, some slightly tougher. You can get things that are translucent, and those sort of things make your prototypes feel more realistic. When you're talking about photopolymers, you really have the choice between an acrylate and an epoxy. And so traditionally, epoxies have been used. They shrink less after you've printed them, so your object will be less warped. It's more likely to remain the shape that you intended and the shape that you printed. However, the objects are more brittle, they're more sensitive to humidity, they are slower to print with, they're more difficult to inkjet if you're interested in that. And actually, about 10% of users have contact dermatitis when exposed to epoxy resins. And so for things like hearing aids, this is increasingly important. And so we've seen the industry transitioning from these epoxies towards acrylate-based photopolymers. Oh, so I already kind of touched on some of the applications of these 3D printed photopolymers. So as I said, in inkjetting, you can use them to make prototypes, props, models. A lot of surgical training models are made in this way because you can create slightly different materials with the right textures to simulate bone and muscle and tissues. And also, several companies have been trying to 3D print shoes in this way. You still can't get quite the properties that you would expect for shoes made in traditional ways, but increasingly you can get combinations of more rigid and more flexible parts. Stereolithography used, as I said, for jewelry, for dental models, for hearing aids, for architectural models. So traditionally these are made using card, cut out and glued together. It's very time consuming, it takes a lot of skill on the part of the architect, and there are whole people employed solely to make architectural models. But increasingly, as architects are designing in CAD software, their models, their ideas are already in the computer. They already have a 3D model, and so it's easier for them to just print it out in 3D. Initially, this was used just to be impressive by the big architectural houses. They can print very large-scale models to show to their clients, but it's been adopted across the industry now. So some of the key people involved in making these photopolymers, still a fairly small industry with a fairly limited number of suppliers. So now I want to move on to talk about thermoplastic filament. This is probably the 3D printing material you're most familiar with. So about 70% of the market by mass is either PLA or ABS. These are normally the easiest to print. They're commonly available in filament form in a wide variety of colors. PLA was really the material of choice when these types of 3D printers came out of the RepRap project. So this is individual hobbyists making their own 3D printers at home as a way to save energy and resources. If you then print in PLA, this is something that you can make from a plant base. And so you're not using a plastic that comes from oil, and it fits with the whole ethos of the RepRap project. So a lot of these printers were designed with that in mind, and it's a continues to hang over into the modern industry. There are now a number of other filaments available. You can get them in things like PET, but there are still some notably absent polymers. So things like polyethylene and polypropylene are still not impossible, but very difficult to find. These materials and these printers are used in a really wide range of industries, traditionally for prototyping, but more and more for tooling, mold making, model making, things like that. We've seen it in kind of automotive, aerospace, increasingly in education. A number of governments across the world have pledged to put a 3D printer into every school. The UK, South Korea, China, Germany have all made this pledge. And that's a huge number of sales of these printers, but it's kind of unlikely that they'll be used often or a lot, and the material sales to these schools are not likely to be huge. The kind of advantages of using these types of printers are that they're cheap, but they are fairly slow, they lack precision, and they lack strength, particularly in the out-of-plane direction. So as you build it up layer by layer, you get reasonable properties in the plane, but between the layers, you often don't get good adhesion, and that's where your object will break apart. Kind of talked about some of these applications already, but mostly used for kind of small, cheap plastic objects, ornaments, toys, things like that. The industrial uses are increasing but remain limited. There are a large number of companies that make these types of filaments. They can now be bought very cheaply off the internet. The price is decreasing all the time. I kind of touched on already some of the available polymers, so PLA and ABS most commonly available, polycarbonate and nylon increasingly available, and a range of other things used mostly in fairly specialist applications. And kind of a lot of the big chemical suppliers in the world do feed into these markets. It's currently not a huge plastics market, in the scale of all the plastics sold in the world, but most people are aware of this as a growing market and tracking it closely. One of the kind of interesting developments in thermoplastic filaments has been the increasing use of new fillers. So people who are using very standard polymers, things like PLA and ABS, and instead of using new chemistries, adding fillers to change the properties. So, a number of interesting things, some of them like wood fiber and bronze added purely for aesthetic reasons. So if you're making a model of something that you eventually intend to make from wood, you can 3D print something that's wood-like and has the look and feel you're going for. Particularly artists reasonably frequently use these types of novel filaments to give a look and feel, but at a much cheaper price point. And then things like graphene, added for the electrical conductivity. You can try and increase the conductivity of your material by loading it with graphene or metallic particles. You can make it just about conductive enough to carry some signals, but it's not really useful for any sort of power application. And then things like magnetic iron can be added in to give it magnetic properties, to increase the range of materials that can be 3D printed and the range of properties you can get from them and the range of functional things you can build. I touched on already the falling price of free market materials. So traditionally, there's been a very large markup on these materials. These materials are typically significantly more expensive than the thermoplastic pellets that they are made from. The cost is falling rapidly as there's been an increase in interest and increase in users. More and more companies are making them, and the price has really crashed. I'm now going to move on to talk very quickly about thermoplastic powders. So mostly nylon, although some polystyrene and some ABS is used. Again, mostly prototyping, but also used in some aerospace applications, some orthopedic implants. The fine powders can be explosive, and so care is needed when handling them. You can get fairly strong, fairly precise items from them fairly quickly. The price per item is considerably more expensive than the other techniques. So I've already kind of touched on some of the applications of these powders. And some of the key people supplying into this market, typically sold in fairly low volumes. Actually, a lot of the machines that use these types of powders are run on the vendor lock-in model. So this is where you buy a machine, you are then locked in to buying your material from that supplier. So this was very common in the 2D printer market. When you buy a printer, you then have to continue to buy your inkjet cartridges from that same manufacturer, and if you buy ink cartridges cheaply from somewhere else, you void the warranty, they're not guaranteed to work, etc. This is fairly common in 3D printing, particularly at the industrial end. The selective laser sintering materials are not strictly vendor lock-in that the companies will allow you to use materials from other places, but they will strongly advise against it. The machines are very finely tuned to work exactly with their powders, and the users don't have much ability to change much about their machines, and so it's fairly difficult for users to buy powders from other places. Just a quick kind of case study of people using these powders. So Boeing have been using 3D printing for over 12 years now. They've had these laser-sintered thermoplastic parts in production for at least 10 years. They have over 20,000 parts in non-critical applications in flying aircraft. They still expect full clearance of flight-critical parts to take considerably longer. And they said that 3D printing any part has to offer a cost saving of 10% to be economically viable because of the increased cost of regulating such a part. And also Dyson, they're a UK manufacturer of things like vacuum cleaners and hand dryers and things. They have a number of 3D printers in-house. Their weekly spend on materials for their 3D printers is $46,000. And nylon powder is 95% of that. They have real difficulty achieving the mechanical properties that they want still, and they have weaknesses and real dimensional instability of their parts. So just quickly going to talk about 3D printable metals. So this is a summary of materials that are currently available to buy to 3D print. Titanium being the most common by a long way, used predominantly in aerospace and in orthopedic implants. So as far as the powders go, you need very fine powders to get good resolution, good surface finish, and to easily melt them together. You need a very narrow size distribution so that you get consistency, so that you can get an even layer of powder during powder spreading. And highly spherical powders are really optimum for this. You also need a very well-controlled purity. Any impurities in your metal powders lead to porosity. Typically, the powders required for selective laser melting are both smaller and have a narrower size distribution than those required for the other techniques, and this makes them more expensive. Again, a number of people who supply into this industry. People like AP&C, who are actually now owned by Arcam, LPW, Sandvik, supplying very kind of traditional engineering metals, things like titanium, aluminium. But then people like Argon, Cooks and Gold, Lagore Group, supplying precious metals, things like gold, silver, platinum, intended for use by the jewelry industry, who have been one of the key adopters of this technology. So, kind of mentioned already, 3D printed metal powders used in aerospace applications, used in implants, particularly acetabular cups in the hip, used for jewelry, and in just about critical aerospace parts. We've seen the first couple of examples begin to be talked about. And so we see that kind of prototyping and orthopedics and non-critical aerospace are fairly well established in printing metals, but things like use in construction and things like electronics are still at a very early stage. No presentation would be complete without talking about GE Aviation. They are printing 114,000 fuel nozzles to use in 6,000 jet engines that will start flying during this year. They melt 20 to 100 micron layers of a cobalt chrome alloy to make these nozzles that were previously made by welding together 18 separate pieces. And the extra design flexibility has allowed them to be 25% lighter. GE were very vocal about this and about their kind of pioneering use of the technology. They've since become a little bit quieter about it. But we have no doubt that other similar aerospace manufacturers are using 3D printing to at least this extent. So I'm now going to move on to talk about some of the emerging materials, some of the things that aren't as commonly available. So carbon fiber is a very commonly used material in engineering, particularly in aerospace and automotive, who are some of the biggest adopters of this additive manufacturing technology. It's possible to chop your carbon fiber and add it to your nylon powder before you selectively laser sinter it. However, chopping your carbon fiber kind of reduces some of the point of it, that it is long strands, and you don't really get all the benefits you might expect. You can also chop your carbon fiber into your thermoplastic filament. It's also possible to take continuous strand carbon fiber and then coat it in nylon, and so you can then pass it through a material extrusion 3D printer, melt the surface of the nylon, stick it together, and build up something that is made from continuous strand carbon fiber in a 3D printer. PMMA is another interesting one. The Dutch company LuxXL can print in PMMA something that is of optical quality in terms of transparency. It's typically very difficult to print transparent materials, although lots of companies will tell you they can. They tend to be quite frosted and maybe not as clear as you would like. In LED lighting, the LED technology evolves so quickly that the luminaire design can't keep up, and often the technology has moved on before the luminaires have caught up. And so being able to quickly produce these optics in customized ways is really important for the growth of this industry. It's also possible to vary the refractive index within the material, within the object, and so you can build light guides and things like that. Another interesting one is silicone. We've kind of talked a bit today about medical applications. So many products are prototyped using cast silicon. Quite often they're 3D printed for kind of visualization testing, but then for form and fit prototyping, silicone often has a better temperature range, a better hardness, a greater durability, and so cast silicone is used afterwards. If you could 3D print in the silicone, you could bring all the advantages of 3D printing to that prototyping stage as well. Also, silicone is used in a number of medical device applications because of its biocompatibility, and so increasing use in the medical and medical research markets. Syringe-based bioprinting, this is again where you inject suspensions of live cells onto some sort of supporting hydrogel material. The supporting hydrogel, often referred to as a bio-ink, can be 3D printed to develop more intricate lattice structures and more customized shapes. There are a number of materials that are used and can be printed. These are often supplied as cartridges so that researchers don't need to mix their own polymers, they don't need to understand the chemistry, they can just print the scaffolding in the shape that they want. Also, UV curing is used for a lot of materials in 3D printing, and this is fine in engineering applications, but you can't use UV curing if you're going to be using it with any living cells. Your UV radiation will damage your living cells, and so you need to look for materials that can be cured using visible light. Metallic glasses is another interesting one. So metallic glasses are amorphous metals without the crystalline structure of ordinary metals. They have high strength, high hardness, low flexibility, very high corrosion resistance, and a very smooth surface finish. This means that they can be used in kind of medical applications and high heat resistance applications. The most common method is currently to cast them, but you need a very expensive metal cast because you need to be able to remove all the heat quickly enough that you form a glass rather than a crystalline structure. Selective laser melting can be used to create these glassy structures. Tanaka Precious Metals Group in Japan have developed a technology, and Heraeus are also planning to start selling a metallic glass powder for this purpose. Wood is another material that we commonly use in construction and manufacture of things like furniture, and so far has not been 3D printed. There's a Swedish research institute that are trying to develop ways of 3D printing with wood. Things like furniture and structural elements. However, wood is a very complicated and highly anisotropic material. It's has a very complex internal structure, and getting a pile of sawdust and sticking it together does not make a tree. We all know of MDF and products like that, which are made from combined sawdust, and this is not the same as real wood. And so 3D printing of wood requires more than sticking together of sawdust. Glass is another material that we commonly use, we make many things out of, and has been very difficult to 3D print because of the very high temperatures involved. MIT Media Labs, who have done a lot of work on 3D printing, have a platform designed to print optically transparent glass. I'm not going to go through the ways that they work, but there are a kind of couple of ways of 3D printing glass. This is really going to open applications not only in things like glassware, ornaments, but also in things like optics and kind of corrosion resistance. So just quickly some conclusions. So the demand for low prices for these materials is driving the market share of the free market value chain, so the number of people buying the materials on the free market at the cheapest price they can find is increasing. The innovation, particularly in the processes and the technologies, is reintroducing vendor lock-in all the time. So if you want to buy a machine that's based on an old technology, you can probably now buy a machine that allows you to buy free market materials. But if you want to buy a machine with the newest processes, it's probably going to be vendor lock-in. Production of actual parts, manufactured parts, rather than prototyping, is really driving volume sales, particularly of metal powders. This has started in low volume, high margin industries, so things like aerospace, orthopedics, but is kind of growing from there. We're beginning to see people in general engineering adopt these technologies. The revenue of the 3D printing industry as a whole is shifting from the technologies, from the machines, into the materials as the installed base is increasing, the number of people buying these materials is increasing all the time. And all these materials keep improving. We see constant innovations, people constantly bringing out materials with different products, with different properties, with different ways of doing things, and it really is evolving very quickly. So that's really everything I wanted to say. Thank you for your attention. I noticed some of you are taking photos. If you'd like a copy of the slides, I'm more than happy to give them to you if you just come and ask me.